All right. Well, today it's great to have Yevgeny Liokumovich from Toronto, who will be talking about the Urathon Width, isoperimetric inequalities, and scalar curvature.
Thank you so much for the invitation, and please feel free to interrupt at any point. I designed my talk to be rather short with anticipation that there will be a lot of discussion. In fact, I don't think I will actually get to scalar curvature, but I hope I will discuss some results about Urathon width and isoperimetric inequalities. And so my talk will be about measuring size of metric space. We will start with some metric space M and some subset of it. Well, the simplest way to measure its size is just to look at the supremum over distances between all points. So that's called the diameter of this set. And in some sense, it measures the one-dimensional spread of our set. But we would like to have some finer ways of measuring, something that would distinguish some large dimensional set from some small dimensional set. And so one of the ways of doing that is to use Hausdorff measure. The way Hausdorff measure is defined is first we introduce something called Hausdorff delta content, which is just looking at our set U and covering it with balls of radius less than delta, and then just summing up these radii to the power of n and taking the infimum over all such sums of radii for all coverings which satisfy this bound. And then we take the limit as the upper bound on the radii in the covering goes to 0. And this gives us Hausdorff measure, n-dimensional Hausdorff measure, and then we can define the n-dimensional Hausdorff dimension, the Hausdorff dimension as the infimum over all n for which the n-dimensional Hausdorff measure is 0. So while we still have this definition of the Hausdorff measure, I want to also define a different way of measuring the size, which is much less known, which is the Hausdorff content, whose definition is much simpler. It's basically considering all coverings by all balls without this restriction on the radii. And the Hausdorff content is quite interesting and often useful in geometry because it sort of disregards the small scale features. For example, if you have a very long and thin torus, and then, but also it has a lot of wrinkles, maybe you attach this very small diameter, you do this connect sum with very small diameter but very large area hyperbolic surfaces, or anything small but very wrinkly, then this torus will have huge area, but at the same time it will have very small two-dimensional Hausdorff content because you can cover it by these balls which contain all of these things. And so in some ways it is sort of one-dimensional because it sits close to a circle. And so if you sum up the squares of radii of these balls, you can make them small, and so the Hausdorff content will be very small compared to Hausdorff measure. So my point is the n-dimensional Hausdorff content is always less than the n-dimensional Hausdorff measure, but sometimes it can be much less. The downside, of course, is that Hausdorff content is not a measure, right? If you, for example, take a disk and then you cut out a smaller disk from it, then the one-dimensional Hausdorff content did not decrease, even though you took out something with non-zero. Still, the best way to cover it is just by one ball. So So it's not additive for disjoint sets. Okay, so with these definitions in mind, let us now change gears and consider yet another way of measuring the size of a metric space, which originally came up in the study of dimension theory in the early 20th century. And this is the Urathon width. If you have a map F from one metric space to another, then you can consider the supremum of the diameter of the fibers of this map. So you just look at the diameter of the largest fiber. In this picture, I drew two nice manifolds, and the fibers are nice submanifolds, but it doesn't have to be so. These preimages can have any dimension, that can be any sort of space, any sort of set. We're just measuring their diameters. And then the k-dimensional Urathon width is defined as the infimum of the Urathon width of all maps from our metric space M to some k-dimensional simplicial complex. So if somehow our metric space can be mapped into a k-dimensional simplicial complex continuously, such that the fibers have small diameters, then it's in some sense k-dimensional, well approximated by a k-dimensional space. So one can observe that, for example, if our metric space is a n-dimensional manifold, then the n-dimensional Urathon width will be 0, because the manifold itself is a simplicial complex. You can map it to itself. Then the preimage is a point, and it has 0 diameter. And then the lower dimensional Urathon width will all be finite if our manifold is compact. It has finite diameter, and then the 0 dimensional Urathon width is just the diameter of that manifold, the map to a point. So you have these immediate inequalities. So this is a very nice geometric way of thinking about it, but that's not how Urathon width was originally defined. Originally, it was defined in terms of coverings. So there's an alternative characterization of Urathon width in the following way. So if you can cover your metric space by open sets, such that each open set has diameter at most W, and the multiplicity of the points that lie in different sets lie at most in k+1 set. So the multiplicity of this covering is at most k+1. Then the Urathon width will be bounded by W, and in the other direction, you can take the k-dimensional Urathon width is equal to the infimum of all W's for which such a covering exists. So at first it looks like a very different definition, completely different from what we described before, but in fact the proof of the equivalence between these two definitions is not too hard. The idea is that if you have a metric space and you consider a covering of this space, it's not a very good picture. So I drew these things too close to each other. Maybe that's better. From this, you can construct a polyhedral complex as follows. Corresponding to each set, you define a vertex in your simplicial complex. Corresponding to a multiplicity 1 set, to multiplicity 2 region, where two sets overlap, you define an edge, and you connect the two vertices corresponding to the sets which overlap. And you keep doing that. And this way you construct a simplicial complex, which is called the nerve of this covering. And then using a partition of unity subordinate to this covering, you can define a map into the simplicial complex constructed in this way. And this map will have a property that preimage of each point in the polyhedral complex will lie in one of those sets. So the size of the fibers will be bounded by this depth. And in the other direction, if you have a map into a polyhedral complex, then you can cover this polyhedral complex by tiny balls, tiny open sets. And if you look at the preimages of these tiny open sets, then they will give you this nice covering with this property. So we have this nice definition, and there are two ways of thinking about it, either as diameters of fibers of a map into a polyhedral complex, or multiplicity of the covering with diameters of open sets control. And so one can use this definition to define a dimension, what's known as the covering dimension of the space, try to in a way that's kind of similar to nice sets like the cube. You could say that my set is n-dimensional if I can cover it with tiny open sets which have overlap at most n, but I cannot cover it with tiny open sets which have if I can cover it with tiny open sets with overlap at most n+1, but I cannot cover it with tiny open sets with overlap n. And Lebesgue covering theorem tells us that the unit cube has exactly this property. The n-dimensional Urysohn width is 0, but the n-1 dimensional Urysohn width is 1. You cannot cover your cube with overlap at most n, and such that all open sets are tiny. And another classical theorem of Shpiran relates the Hausdorff measure to this covering measure. And it says that if the Hausdorff measure is 0, then the covering measure is also 0. Then then it's possible to map into an n-1 polyhedral complex, or construct an n-dimensional, or construct a covering with a multiplicity at most n by small sets.
Yevgeny, there's a question by Barish. He's asking, can you do this intrinsically? And I presume he was referring to the theorem, the implication by Lebesgue covering theorem. Barish, can you?
Yeah, can you define this covering intrinsic balls?
Yes, I think these are. Well, I'm not sure if I understand the question correctly, but these coverings are intrinsically defined on
so you are not embedding
space. Yes.
Yeah, so you are not talking about any embedding. You are just talking about abstract space.
Yes, we are talking just about an abstract metric space at this moment. Yes. Yeah. So the main theorem that I'm going to present is the quantitative version of Screwdriving Theorem. And the result, so again, the Screwdriving Theorem says that if the Hausdorff measure is equal to 0, then the Urysohn width is equal to 0. And we will show that if the Hausdorff measure is small, then the Urysohn width also has to be small. So our theorem is Boris Lishak, Alex Nabutovsky, and Yevgeny Rotman. And then later, a different proof was given by Panos Papasoglu, is that if you have a compact metric space X, then the n-1 dimensional Urysohn width of X is bounded by the Hausdorff content. And if you remember, the Hausdorff content is bounded by the Hausdorff measure of X. There is a more general version of this result where we do not assume that this space is compact, but only locally compact. And instead of the Hausdorff content of the whole set, we look at the Hausdorff content of balls of some fixed radius. And then we also get a bound on the Urysohn width. But that statement is a little bit more technical. So if there is interest, I could describe it, but I wanted to first try to describe and motivate this result. So this result was in fact a conjecture of Larry Guth, who proved a similar bound where instead of a metric space X, you have a manifold, and instead of the Hausdorff content, you have volume. And motivation for this came from systolic geometry. In fact, this inequality immediately implies certain interesting inequalities relating the length of a shortest non-contractible loop in a large class of manifolds and the volume of that manifold, or in our case, the Hausdorff content of that manifold. N-dimensional Hausdorff content, where n can now be different from the dimension of the manifold. That's also something that I could describe if there is interest and if there is time. Now let me talk a little bit about the proof of this result. The idea is similar to what I described earlier, of how we relate the covering definition of Urysohn width and the mapping definition of Urysohn width. So if we have a metric space and we can construct a certain covering with some special properties, we can define the nerve of the covering. And let me draw this nerve separately here as a subcomplex of some large dimensional cube. Then we can use partition of unity, and if our covering was chosen with some special nice properties, then we can map it. We can map our metric space into this cube. This map is going to be Lipschitz, and the image will have Hausdorff content controlled in terms of the Hausdorff content of the original metric space. And then the idea that also comes from Larry Guth's proof is to start pushing this image under this map into the lower and lower dimensional skeleton of this cube, all the way until we push it into the n-1 dimensional skeleton. And in doing so, we want to control, first of all, that the Hausdorff content does not increase by much after each deformation, and that the path that these deformations follow is not too long, so that when we take the pre-images, we have control on the diameter of the fibers. And to iteratively do this deformation, what we basically need is an isoperimetric inequality. If you remember, there's this classical Federer-Fleming isoperimetric inequality, which basically is proved by picking some grid, some k-dimensional skeleton, and then pushing into that skeleton from a random point. But that inequality, if you remember, the constant, the amount, the size of the filling and the displacement all depend on the dimension of the ambient space. And in our case, a priori, we don't have any bound on the multiplicity of our covering that we choose. So the dimension can be very, very large. Somehow we need an isoperimetric inequality where these deformations only depend on the dimension of the set itself. not on the dimension of the ambient set.
Yevgeny, could you explain the initial map F again into the cube? I guess since you were using the nerve, I was expecting a map into a simplicial complex, but.
Right. So I don't think there is a substantial difference between choosing a simplicial complex and the cube. Cubes are a little bit easier geometrically to work with. And in fact, this will be not cubes, but how do you call the cubes whose different sides have different lengths? These are parallelepipeds. That's what they are. So to each for each set, we associate an interval whose length is equal to the radius of the ball. And the balls in our covering will have very different sizes. Basically, the way we choose balls is we look at how Hausdorff content changes inside the ball as we increase it, and we pick a certain threshold where the change sort of starts to slow down. Then we use co-area inequality that we prove for Hausdorff content to control the size of the intersection of the boundary, the Hausdorff content of the intersection of the boundary of the ball. So some balls are going to be tiny and some balls are going to be large, depending on the shape of our metric space. And so we will have these parallelepipeds of different sizes, with different sides having different sides. And then we basically have a partition of unity corresponding and to each, and basically we map into, so we'll have phi1, phi2, basically this is going to be the corresponding maps in our partition of unity. And the covering will be locally fine. I mean, right, so we actually don't control the multiplicity of the set. So we may potentially have a lot of overlap, and so we may potentially have a lot of non-zero. You know, we may potentially have faces very, very large. At some point, we actually think of this as lying in an infinite dimensional Banach space. We don't have to, but the point is that we have no control on how large this cubical complex is.
Great, thanks.
So there is a classical isoperimetric inequality like this, which allows us to fill cycles by chains in a way that the size only depends on the dimension of the cycle, not on the dimension of the ambient space. So say you have this n-dimensional cycle in R capital M, and then the classical isoperimetric inequality of Michael and Leon Simon says that we can find a chain tau filling this cycle, so boundary of tau is equal to z, and moreover, the volume, the n+1 dimensional volume of tau is controlled in terms of the n-dimensional volume of z, and there's no dependence on the ambient dimension, unlike the Federer-Fleming isoperimetric inequality. So this inequality was later revisited by Gromov in his proof of the systolic inequality. And in his context, he actually needed to consider an infinite dimensional Banach space instead of Rn, because he took the manifold and he used the Kuratowski embedding into the space of L infinity functions. And he proved a similar inequality in that setting. And there is a more recent proof by Stefan Wenger, which is very nice and short of this result. And so what we proved to do this deformation to prove this Urathon width inequality is something quite similar, but for metric spaces instead of chains, and for Hausdorff content instead of volume. Well, one way of looking at this is in terms of Lipschitz cycles and chains, but you can also specify the topology of it. So you can ask the following, you can change the formulation of the isoperimetric inequality as follows. So say you're given some chain or simplicial complex X, and this is your boundary of X. And then you have a map Z from the boundary of X into Rn. And then you want to find the filling, but really it's just an extension. Extension F from X into Rn. That is the restriction of F to the boundary of X is equal to Z, such that, you know, the volume of the image is controlled. So you can reformulate this inequality in this way, and in fact, the original proofs can be modified so that you actually have this statement. And when you reformulate it like that, then it doesn't really become, it's not even important that we're looking of an extension from the boundary. We could consider any subset and try to find an extension of a map from any subset. And so in the metric space context, we prove this kind of isoperimetric inequality, that if you have some Banach space, possibly infinite dimensional, and you have a map of a metric space X, and sorry, you have a metric space X, and you have a subset Y, and you have a map from Y into B, and you have control on the Hausdorff content of this image. And let's assume that the n-dimensional Hausdorff content is not zero. If it is zero, then we can make an extension with arbitrarily small n plus 1 Hausdorff content, but there's no nice compactness here, so maybe not necessarily zero. So assume that the n-dimensional Hausdorff content of F is not zero, then we can construct the extension to the map from all of X into the Banach space, and the n plus 1 dimensional Hausdorff content of F of X is bounded by the n-dimensional Hausdorff content of little f of Y. F restricted to Y is equal to 2. So that's the kind of the main part of the proof, the most difficult part of the proof in our result. And I think it has independent interest because in various directions. One direction that for this original problem and for the systolic inequality problem, but one could think of this constant C of n, one could try to understand what is the optimal sharp constant here. And I think it's even reasonable to conjecture that this constant may be 1. And if you can prove that this constant is 1, then you get really nice, you get very close to optimal systolic inequalities. And that would be quite interesting because that's something people have thought for a long time about. There is additional result, which is also, you know, takes a big part of our paper, is that in addition to the isoperimetric inequality, you want to prove a filling radius inequality. You want to say that this image f of x not only has small Hausdorff content, but will actually lie close to the boundary, close to little f of y. Except possibly for topological reasons, you cannot make all of it lie close to little f of y, but you can make all of the large part of it lie close to f of y. That is, except for a set of 0 Hausdorff n+1 dimensional Hausdorff content, everything else will lie in a radius which is bounded by the n-dimensional Hausdorff content of little f of y. And that's kind of important for our Urathon width inequality, because we want to make sure that as we do these deformations, these sets don't move very much. So in the end, we have control control on the diameter. Right. So I guess I've been rushing through a lot of these results, and I'll be happy to make questions or take it in any direction that the audience may be interested in.
Okay, can I ask questions now?
Anybody?
One of the main reasons we are very interested in this result is n-1 with relation with the Gromov filling radius. So Facundo and his collaborators show that the Gromov filling radius is so you can have the persistent homology, the Beatrice complexes and persistent homology is very closely related to the persistence of the lifespan of the any homology class with the Gromov filling radius, and there is this conjecture about n-1 Urysohn width bounds Gromov filling radius of any homology class, any n-dimensional manifold homology class. So if I give you n manifold, its Gromov filling radius, whatever it is a lower bound for its persistence in viatory Slips complex language. This is Facundo and his collaborators' result. They embed this in a manifold to the Nabutovsky embedding, and then they find a very nice relation there. And in metric geometry, there is this very important conjecture. Gromov filling radius is bounded by n-1 Urysohn width. This is, I mean, it's not proven yet, but your result is somewhat very related with this. Can you elaborate on that, and can you give some ideas? Do you know anything about this?
So
Gromov filling radius versus n-1 Urysohn width.
Right. So I believe it follows from some original papers of Gromov from his free filling Riemannian manifolds that the filling radius, the one that's defined in terms of the Kuratowski embedding of manifold M, is bounded by right, so it's bounded by I can't quite remember the constant, but it's some very simple constant, one third by Urysohn width of the manifold M, and you can actually put any Urysohn width for K here is between n-1 and 1. So I believe that this was proved in Gromov's filling radius, and also this bounds the systole of M, something that Gromov observed, where the systole is the length of the shortest non-contractible loop for a certain class of manifolds. This holds for essential manifolds. And so this is why our original interest was in this problem. This is a motivation for a lot of this. So let me just recall that the systole of a manifold M is the infimum of a whole length of gamma, where gamma is a non-contractible curve in M. And so Gromov's famous result from his filling Riemannian manifolds is that if M is an essential manifold, then systole of M is less or equal than a constant that depends only on the dimension of M times the volume of M to the power 1 over n. And here essential means that, so in particular, one example of essential manifolds are all aspherical manifolds like tori. But more generally, what it means is that if you take your manifold and you construct the classifying map by killing all the high homotopy groups, so you fill in all the high homotopy groups and you get the manifold into the Eilenberg-MacLane space, then the n-dimensional, the map on the n-dimensional homology is non-zero. So the map is kind of essential, or maybe more generally, the map doesn't factor through some lower dimensional space, lower dimensional polyhedral complex. So basically, if you look at a map from X to K pi 1, K pi 1 X 1 to an Eilenberg-MacLane space, and then so this is my X or M. Then it doesn't factor through some n-1 dimensional complex. So there is no, so Q is not homotopic to Q prime, to map Q prime. And so from our Hausdorff content result, what one can do is one can modify this definition and define something called M essential, where now you look at, instead of n-1 dimensional complex, you look at m-1 dimensional polyhedral complex. And your map is M essential if it doesn't factor through an m-1 polyhedral complex. And then our conclusion will be that the system of M is bounded by a constant, which depends only on little m, times the m-dimensional Hausdorff content of M to the power 1 over M. And now this M can be smaller than the dimension. So M is somewhere between M and 1. It's n-dimensional manifold. So for example, a manifold like a 2 torus cross S3 connects some with S2 cross S3. This manifold is not essential in Gromov's sense, but it is too essential in our sense. And so for such manifolds, we obtain an inequality in terms of the two-dimensional Hausdorff content of this manifold on the length of the system. And it's also more general than Gromov's inequality because Hausdorff content is smaller than the volume. Somehow disregards the wrinkliness on the small scale. And why this is possible is precisely because of the string inequality that Gromov related the Urysohn width to the filling radius and the filling radius to the system of the manifold.
Thank you.
I have a question. So one of your results along the way, you said that if you could, it's reasonable to conjecture that the constant was 1. And if so, then you might be able to prove optimal constants in, Gromov's systole inequality. So that's the one that you had just written down here before you.
Exactly. That's the one.
But is it the case that very little is known about the optimal constants, either in Gromov's constants or context, and also very little is known in your context as well, your generalization? Right. So the original, there was a question of how this depends on the dimension in the original Gromov's question. And I think original Gromov's constant was super exponential in the dimension. And then eventually there was a series of improvements by different people. And Alex Nabutovsky, based on our work, I think has the best constant, but I think it's still not the right power. I can't remember I think it has to be square root, and it is linear what he proved. Or maybe what he proved is square, but it has to be linear. So there's a square root. There's still a square root to go, I believe. Right, and I think if one can prove this result, the isoperimetric inequality with optimal constant, then one may be able to get rid of that square root. Another direction why optimal constant might be very, very important is the connection with scalar curvature. So people talk about, so there is a reformulation of our result where instead of taking the Hausdorff content of the whole manifold, we look at the Hausdorff content of balls of a fixed radius. And this reminds people of a lower bound for scalar, of a positive lower bound for scalar curvature, because if you write in the Riemannian manifold, if you write the volume of a ball of radius r, and you just divide it by the Euclidean volume of the same radius, then so the first term is 1, and then you get the term which is minus a constant times the scalar curvature at that point, p times r squared, plus a term of order r to the 4th, plus terms of high order. And so you know that, for example, for a compact manifold, there is a radius, there is a scale on which all balls are smaller than Euclidean balls. If your scalar curvature of M is greater than some constant, is positive, then you know that at some scale, all of your balls have smaller volume than Euclidean. And so if you could prove an analog of our result with optimal constants, where just being slightly smaller than Euclidean implies that you actually have small Urysohn width, then that would be really cool, because one of the conjectures, so there's a Gromov's conjecture, that the scalar curvature is a kind of a very weak curvature invariant, unlike sectional or Ricci curvature. And if you take any manifold whatsoever and multiply it by S2 of small radius, small r, then you will make its scalar curvature positive. And Gromov's conjecture is that actually all manifolds of positive scalar curvature are in some sense geometrically similar. Look this way. So Gromov's conjecture is that the n minus 2-dimensional Urysohn width, so if scalar curvature of M is positive, and M doesn't need to be compact, but if it's uniformly positive, then the n minus 2-dimensional Urysohn width of M is finite, or even bounded by a constant, bounded by some function of epsilon. But so this is open for n minus 2. It's also open for n minus 1. Both of these are open, except for the case of 3-dimensional manifold, where this is known, and under some additional assumptions, if for 4- and 5-dimensional manifolds, you can prove results like that if their pi2 is 0, and for 5-dimensional, if their pi2 and pi3 are 0. So if you could, strengthen some of these inequalities to optimal constants, then you would get these. Then you may be very close to getting this Gromov's conjectures, but this is even stronger because the scalar curvature just tells you that on some scale, your balls have volume smaller than the Euclidean, and these inequalities would tell you with these results with optimal inequalities could tell you that if on any scale your balls look smaller than Euclidean, then your manifold globally looks like it's actually smaller dimensional.
Thanks.
Do we have any more questions or comments for Yevgeny?
One more question. If no one is asking. Okay, Yevgeny, so other than Urysohn width, I mean, so we are really interested in this lower bound for the Gromov filling radius. Is there any other metric invariant or something like that is a conjecture or to bound the Gromov filling radius by using the measurements on the manifold somehow, not the width, but something else maybe, to lower bound the Gromov, because it's a very interesting invariant and it's very closely related with the life of a persistence homology and the lifespan of this vital series complexes.
Right.
Can you think of any conjecture which might be useful in this way? Lower bound for the Gromov filling radius. Systole is okay, but systole is very weak in some sense.
Right.
Urysohn n-1 width is very nice, but it's very hard to get this. Yeah, but some other in some other metric geometry.
But you're interested in the
Lower bound.
lower bound for
Yes. Upper bound is fine, but lower bound is
lower bound, right?
very interesting for us.
That's a good question.
I know in minimal surfaces, in other fields, there are lots of different approaches to this kind of questions, but maybe there's something we don't know happening in the metric geometry.
Yeah, I think it's tricky. Yeah, I agree. It's tricky to prove lower bounds for filling radius. I don't have any good suggestions at the moment.
Okay. Yeah. You know, if something comes up, just let us know.
I will. I will. Yes. Yeah, it's very interesting that it has connections to this topological data analysis. It's pretty cool.
Yeah. And thank you very much for the nice talk. We couldn't clap you, but
Thank you.
Well, yeah, we, if there are, I wonder if there are any more comments or questions for Yevgeny. We can maybe take a few seconds to see if anyone else wants to jump in. And if not, yeah, we typically just thank the speaker by clapping. This is the best.
Thank you.
Thank you. Thank you very much for your wonderful talk, Yevgeny.
Thank you.